Hello, America. My name is Dylan John, and you are listening to Nature and the Nation. This podcast uses the format of a book review to explore the intersection of philosophical naturalism with paleoconservatism within the framework of the revitalization of the Republican Party. We will be exploring politics, philosophy, psychology, economics, and sociology through a wide variety of books published both recently and historically. Thank you for tuning in. For today's episode, we will be reading Richard Dawkins' book called The Selfish Gene. This was written in 1976, and it was immensely popular when it came out. And it's still immensely popular. The book I have is a reprint from 1989, but nothing substantial has changed from 76 to 89. And essentially it's a book about evolution and about genes and about behavior, primarily behavior of living things. So it touches on human behavior, but it mostly talks about animal behavior. It talks a little bit about plants as well. It's really about the process that animals and living creatures use to enhance the survivability of their genes. And so I'm doing this book today because I want to sort of dig into the philosophical naturalism a little bit more in the framework of the podcast. I've talked an awful lot about politics and different aspects of sociology and whatnot. I've talked a little bit about human nature. I've talked a little bit about evolution, but I think that it's important for me to really dig into this a little bit deeper. So this book, as well as a few of the upcoming books, are going to start spelling out more specifically how the evolutionary process works, in particular how evolution affects human behavior, a little bit of an understanding of how the human mind works, and we'll be tying all these things in together with this book and a couple of the next books, because when I talk about philosophical naturalism being a part of my podcast, what I'm really aiming at here is not so much of maybe a metaphysical understanding of reality, although that's certainly part of it and that's kind of fundamental to it. But the reason I talk about this is because I want to understand human beings and human behavior and why we behave the way we do and what sort of parameters there are within which we operate and what can we expect people to do. What can we expect our own nation and our neighbors to do, and what can we expect foreign people and foreign nations to do? Can we have some kind of an understanding about human nature? I mean, the more deep our understanding of human nature, the better our political systems will be. And to understand human nature, we really need to understand what we are, how we became the way we are, and what forces drive us. To really understand that, we need to begin to understand evolution, because evolution is fundamental to our behavior. And that's sort of what I want to start getting into today. So, in this book, he talks. I mean, this is I'll just say this is a fantastic book. It's obviously 1976, so you're talking like, over 40 years old. But the contents of this book are still every bit as applicable today. I don't believe that anything in this book has been disproved by the intervening 40 years. I'm fairly certain that everything in here is still legitimate. Now, he makes some assertions that are a little bit more in line with his opinion, but mostly it's scientific fact. And where he's conjecturing, he says so. So like his explanation for the origin of life, which is something that I want to talk about, he basically says, we don't know exactly that this is how life began, but this is what it seems like. This is his hypothesis. And there are a few other hypotheses out there And I guess that in one of his other books, he introduces an alternate version of this theory of how life began, but the one in this book seems pretty on point to me, and the extent to which the origin of life deviates from this, it doesn't deviate dramatically, right? It's not he's not, and in science is not going to switch up and postulate some supernatural divine creation of humanity, barring some real radical change in the evidence that we draw from. So this is essentially the or one of the reigning theories in science as to how life began. And so I'm going to talk about that and the implications that we can draw from it. And it's really the implications that are the most important part of it. So I'm only going to talk about a few sections. That is one of them. And then the other section I want to talk about is a little bit later on when he introduces the idea of the evolutionarily stable strategy. Those are the main areas I want to talk about. There's a lot more in this book. He talks about mating and child rearing and in-group kin selection and things like that. He talks about altruism. He talks about a lot of stuff. I really recommend you pick this book up and read it. I'm not going to cover everything he talks about. Some of the things in here I'm going to talk about at more length in later books that I review. And so I'm going to basically skip over those sections for now. I actually have a few books lined up that are going to cover some of those points in some more specific detail. But it's those first concepts, especially the evolutionarily stable strategy, that I want to really dig into. So let me go ahead and start reading from the first section here, when he sort of talks about the origin of life, and then what are the important points. I'll talk afterwards about what the important points are that we can kind of extrapolate from this theory. So he says, quote, "The account of the origin of life that I shall give is necessarily speculative. By definition, nobody was around to see what happened. There are a number of rival theories, but they all have certain features in common. The simplified account I shall give is probably not too far from the truth. We do not know what chemical raw materials were abundant on Earth before the coming of life, but among the plausible possibilities are water, carbon dioxide, methane, and ammonia, all simple compounds known to be present on at least some of the other planets in our solar system. Chemists have tried to imitate the chemical conditions of the young Earth. They have put these simple substances in a flask and supplied a source of energy, such as ultraviolet light or electric sparks, artificial simulation of primordial lightning. After a few weeks of this, something interesting is usually found inside the flask: a weak brown soup containing a large number of molecules more complex than the ones originally put in. In particular, amino acids have been found, the building blocks of proteins, one of the two great classes of biological molecules. Before these experiments were done, naturally occurring amino acids would have been thought of as diagnostic of the presence of life. If they had been detected on, say, Mars, life on that planet would have seemed a near certainty. Now, however, their existence need imply only the presence of a few simple gases in the atmosphere and some volcanoes, sunlight, or thundery weather. More recently, laboratory simulations of the chemical conditions of Earth before the coming of life have yielded organic substances called purines and pyrimidines. These are the building blocks of the genetic molecule DNA itself. Processes analogous to these must have given rise to the primeval soup, which biologists and chemists believe constituted the seas some 3,000 to 4,000 million years ago. The organic substances became locally concentrated. perhaps in drying scum round the shores, or in tiny suspended droplets. Under the further influence of energy, such as ultraviolet light from the sun, they combined into larger molecules. Nowadays, large organic molecules would not last long enough to be noticed. They would be quickly absorbed and broken down by bacteria or other living creatures, but bacteria and the rest of us are latecomers, and in those days, large organic molecules could drift unmolested through the thickening broth. At some point, a particularly remarkable molecule was formed by accident. We will call it the replicator. It may not necessarily have been the biggest or the most complex molecule around, but it had the extraordinary property of being able to create copies of itself. This may seem a very unlikely sort of accident to happen. So it was. It was exceedingly improbable. In the lifetime of a man, things that are improbable can be treated for practical purposes as impossible. That is why you will never win a big prize on the football pools. But in our human estimates of what is probable and what is not, we are not used to dealing in hundreds of millions of years. If you filled in pools coupons every week for 100 million years, you would very likely win several jackpots. Actually, a molecule that makes copies of itself is not as difficult to imagine as it seems at first, and it only had to arise once. Think of the replicator as a mold or template. Imagine it as a large molecule consisting of a complex chain of various sorts of building block molecules. The small building blocks were abundantly available in the soup surrounding the replicator. Now suppose that each building block has an affinity for its own kind. Then, whenever a building block from out of the soup lands up next to a part of the replicator for which it has an affinity, it will tend to stick there. The building blocks that attach themselves in this way will automatically be arranged in a sequence that mimics that of the replicator itself. It is easy then to think of them joining up to form a stable chain, just as in the formation of the original replicator. This process could continue as a progressive stacking up layer upon layer. This is how crystals are formed. On the other hand, the two chains might split apart, in which case we have two replicators, each of which can go on to make further copies. A more complex possibility is that each building block has affinity not for its own kind, but reciprocally for one particular other kind. Then the replicator would act as a template, not for an identical copy, but for a kind of negative, which would in turn remake an exact copy of the original positive. For our purposes, it does not matter whether the original replication process was positive-negative or positive-positive, though it is worth remarking that the modern equivalents of the first replicator, the DNA molecules, use positive-negative replication. What does matter is that suddenly a new kind of stability came into the world. Previously, it is probable that no particular kind of complex molecule was very abundant in the soup because each was dependent on building blocks happening to fall by luck into a particular stable configuration. As soon as the replicator was born, it must have spread its copies rapidly throughout the seas, until the smaller building block molecules became a scarce resource, and other, larger molecules were formed more and more rarely. So we seem to arrive at a large population of identical replicas. But now we must mention an important property of any copying process. It is not perfect. Mistakes will happen. I hope there are no misprints in this book, but if you look carefully, you may find one or two. They will probably not seriously distort the meaning of the sentences because they will be first-generation errors. But imagine the days before printing, when books, such as the Gospels, were copied by hand. All scribes, however careful, are bound to make a few errors, and some are not above a little willful improvement. If they all copied from a single master original, meaning would not be greatly perverted, but let copies be made from other copies, which in their turn were made from other copies, and errors will start to become cumulative and serious. We tend to regard erratic copying as a bad thing, and in the case of human documents, it is hard to think of examples where errors could be described as improvements. Anyway, as we shall see, erratic copying in biological replicators can, in a real sense, give rise to improvement, and it was essential for the progressive evolution of life that some errors were made. we do not know how accurately the original replicator molecules made their copies. Their modern descendants, the DNA molecules, are astonishingly faithful compared with the most high-fidelity human copying process. But even they occasionally make mistakes, and it is ultimately these mistakes that make evolution possible. Probably the original replicators were far more erratic, but in any case we may be sure that mistakes were made, and these mistakes were cumulative. As miscopyings were made and propagated, the primeval soup became filled by a population not of identical replicas, but of several varieties of replicating molecules, all descended from the same ancestor. Would some varieties have been more numerous than others? Almost certainly yes. Some varieties would have been inherently more stable than others. Certain molecules, once formed, would be less likely than others to break up again. These types would become relatively numerous in the soup, not only as a direct logical consequence of their longevity, but also because they would have a long time available for making copies of themselves. Replicators of high longevity would therefore tend to become more numerous, and other things being equal, there would have been an evolutionary trend toward greater longevity in the population of molecules. But other things were probably not equal, and another property of a replicator variety that must have had even more importance in spreading it through the population was speed of replication, or fecundity. If a replicator molecule of type A makes copies of themselves on average once a week, while those of type B make copies of themselves once an hour, it is not difficult to see that pretty soon type A molecules are going to be far outnumbered, even if they live much longer than B molecules. There would therefore probably have been an evolutionary trend toward higher fecundity of molecules in the soup. A third characteristic of replicator molecules, which would have been positively selected, is accuracy of replication. If molecules of type X and type Y last the same length of time and replicate at the same rate, but X makes a mistake on average every 10th replication, while Y makes a mistake only every 100th replication, Y will obviously become more numerous. The X contingent in the population loses not only the errant children themselves, but also all their descendants, actual or potential. If you already know something about evolution, you may find something slightly paradoxical about the last point. Can we reconcile the idea that copying errors are an essential prerequisite for evolution to occur with the statement that natural selection favors high copying fidelity? The answer is that although evolution may seem, in some vague sense, a good thing, especially since we are the product of it, nothing actually wants to evolve. Evolution is something that happens willy-nilly, in spite of all the efforts of the replicators, and nowadays of the genes, to prevent it happening. Jacques Monod made this point very well in his Herbert Spencer lecture, after Riley remarking, "Another curious aspect of the theory of evolution is that everybody thinks he understands it." To return to the primeval soup, it must have become populated by stable varieties of molecules. Stable in that either the individual molecules lasted a long time, or they replicated rapidly, or they replicated accurately. Evolutionary trends toward these three kinds of stability took place in the following sense. If you had sampled the soup at two different times, the latter sample would have contained a higher proportion of varieties with high longevity, fecundity, copying fidelity. This is essentially what a biologist means by evolution when he is speaking of living creatures, and the mechanism is the same, natural selection. Should we then call the original replicator molecules living? Who cares? I might say to you, Darwin was the greatest man who has ever lived, and you might say, no, Newton was. But I hope we would not prolong the argument. The point is that no conclusion of substance would be affected, whichever way our argument was resolved. The facts of the lives and achievements of Newton and Darwin remain totally unchanged whether we label them great or not. Similarly, the story of the replicator molecules probably happened something like the way I am telling it, regardless of whether we choose to call them living. Human suffering has been caused because too many of us cannot grasp that words are only tools for our use, and that the mere presence in the dictionary of a word like living does not mean it necessarily has to refer to something definite in the real world. Whether we call the early replicators living or not, they were the ancestors of life. They were our founding fathers. The next important link in the argument, one that Darwin himself laid stress on, although he was talking about animals and plants, not molecules, is competition. The primeval soup was not capable of supporting an infinite number of replicator molecules. For one thing, the Earth's size is finite, but other limiting factors must also have been important. In our picture of the replicator acting as a template or mold, we supposed it to be bathed in a soup rich in the small building block molecules necessary to make copies. But when the replicators became numerous, building blocks must have been used up at such a rate that they became a scarce and precious resource. Different varieties or strains of replicator must have competed for them. We have considered the factors that would have increased the numbers of favored kinds of replicator. We can now see that less favored varieties must actually have become less numerous because of competition, and ultimately many of their lines must have gone extinct. There was a struggle for existence among replicator varieties. They did not know they were struggling or worry about it. The struggle was not conducted with any hard feelings, indeed without feelings of any kind, but they were struggling in the sense that any miscopying that resulted in a new, higher level of stability or a new way of reducing the stability of rivals was automatically preserved and multiplied. The process of improvement was cumulative. Ways of increasing stability and of decreasing rivals' stability became more elaborate and more efficient. Some of them may even have discovered how to break up molecules of rival varieties chemically and to use the building blocks so released for making their own copies. These proto-carnivores simultaneously obtained food and removed competing rivals. Other replicators perhaps discovered how to protect themselves, either chemically or by building a physical wall of protein around themselves. This may have been how the first living cells appeared. Replicators began not merely to exist, but to construct for themselves containers, vehicles for their continued existence. The replicators that survived were the ones that built survival machines for themselves to live in. The first survival machines probably consisted of nothing more than a protective coat. But making a living got steadily harder as new rivals arose with better and more effective survival machines. Survival machines got bigger and more elaborate, and the process was cumulative and progressive. Was there to be any end to the gradual improvement in the techniques and artifices used by the replicators to ensure their own continuation in the world? There would be plenty of time for improvement. What weird engines of self-preservation would the millennia bring forth? 4,000 million years on, what was to be the fate of the ancient replicators? They did not die out, for they are past masters of the survival arts, but do not look for them floating loose in the sea. They gave up that cavalier freedom long ago. Now they swarm in huge colonies, safe inside gigantic lumbering robots, sealed off from the outside world, communicating with it by tortuous, indirect routes, manipulating it by remote control. They are in you and in me. They created us, body and mind, and their preservation is the ultimate rationale for our existence. They have come a long way, these replicators, and we are their survival machines." End quote. So, again, he doesn't know exactly that what he's describing is exactly what happened, but I think that's probably about as close as it gets to what happened. The DNA inside ourselves that defines the shape and nature of ourselves, that is the unit that is replicating itself through the course of evolution. And when you procreate and have children, you're passing on the DNA. Your function is, you're not passing on yourself. You can't pass on yourself. You live and you die. But what is passed on to your children is a portion of your DNA, a collection of your genes. Not all of your genes, but some of your genes are passed on, and replicas of them are passed on to your children. And so the DNA and the genes are these perpetually replicating molecules that use humans and animals and living things to protect them from destruction and facilitate their replication. So that what he's saying is that the genes and the DNA molecules and the sections of DNA molecules that specify certain behaviors, these are the replicators. These are the units of selection, not people. Evolution isn't deciding this person lives, that person dies, this person passes on, this person procreates, that person doesn't procreate. I mean, it is, but that's not really what's happening so much as the process of evolution is like this gene passes on, this other gene does not pass on. This gene has replication opportunities, and this other gene does not have replication opportunities. If you die without procreating, the particular array of genes that you have do not replicate. They end with you. Your body breaks down, the DNA breaks down, those DNA molecules lose their capacity to replicate. Those genes and DNA molecules that successfully replicate themselves inevitably become more numerous, so that you as a living thing are the survival machine of genes. And genes are the unit of selection, not people. And Dawkins is also very adamant that he's against group selection. Elsewhere in this book, he talks about how people will propose that, well, this group or this tribe of people would have this quality, and that tribe would have that quality. And if tribe A's quality enables them to survive better than tribe B, then tribe A will thrive and procreate and tribe B will not. That's the group selection theory. And Dawkins is very adamant that it might look that way from the outside, but the group is not the unit of selection. The gene is. So that the gene that has whatever quality that would then apply to the group, that gene replicates itself because it is in a group of people or kin that have the same thing. And so that a mutant gene that might potentially bring the group down, but will operate well to its own advantage, will thrive within the group. Even though it may weaken the group, it strengthens the gene of the individual. It strengthens the life of the individual that holds the gene, and therefore increases the replication possibilities of that individual gene, even though it may work at odds with the interests of the group. So that in that way, group selection is actually just the aggregate of gene selection strategies that work well together. That's essentially his argument against group selection. And the next part that I want to read actually gets into that a little bit more, in a little bit more detail, when he starts talking about the evolutionarily stable strategy. This section isn't really about group selection. It's more, well, it's in the chapter on aggression. And the example that he uses to illustrate this is really interesting, and it kind of talks about aggression strategies. Because he's talking about, like in the part beforehand, that I'm not going to read the part, but he's talking about, elephant seals in conflict with each other over access to mates. And, the seal needs to decide, do I attempt to battle another male elephant seal for access to mates, or to go try to feed more, acquire more food, get larger, maybe fight and attack at a later time? There are different strategies that any living creature may engage in as to whether or not to fight another living creature for access to procreation and resources. And so The determination of what that strategy will be is essentially what he's talking about in this section. So here he says, quote, "The decision whether or not to fight should ideally be preceded by a complex, if unconscious, cost-benefit calculation. The potential benefits are not all stacked up on the side of fighting, although undoubtedly some of them are. Similarly, during a fight, each tactical decision over whether to escalate the fight or cool it has costs and benefits, which could, in principle, be analyzed. This has long been realized by ethologists in a vague sort of way, but it has taken J. Maynard Smith, not normally regarded as an ethologist, to express the idea forcefully and clearly. In collaboration with G. R. Price and G. A. Parker, he uses the branch of mathematics known as game theory. Their elegant ideas can be expressed in words without mathematical symbols, albeit at some cost in rigor. The essential concept Maynard Smith introduces is that of the evolutionarily stable strategy, an idea that he traces back to W. D. Hamilton and R. H. MacArthur. A strategy is a pre-programmed behavioral policy. An example of a strategy is attack opponent. If he flees, pursue him. If he retaliates, run away. It is important to realize that we are not thinking of the strategy as being consciously worked out by the individual. Remember that we are picturing the animal as a robot survival machine with a pre-programmed computer controlling the muscles. To write the strategy out as a set of simple instructions in English is just a convenient way for us to think about it. By some unspecified mechanism, the animal behaves as if he were following these instructions. An evolutionarily stable strategy, or ESS, is defined as a strategy which, if most members of a population adopt it, cannot be bettered by an alternative strategy. It is a subtle and important idea. Another way of putting it is to say that the best strategy for an individual depends on what the majority of the population are doing. Since the rest of the population consists of individuals, each one trying to maximize his own success, the only strategy that persists will be one which, once evolved, cannot be bettered by any deviant individual. Following a major environmental change, there may be a brief period of evolutionary instability, perhaps even oscillation in the population, but once an ESS is achieved, it will stay. Selection will penalize deviation from it. To apply this idea to aggression, consider one of Maynard Smith's simplest hypothetical cases. Suppose there are only two sorts of fighting strategy in a population of a particular species, named hawk and dove. The names refer to conventional human usage and have no connection with the habits of the birds from whom the names are derived. Doves are in fact rather aggressive birds. Any individual of our hypothetical population is classified as a hawk or a dove. Hawks always fight as hard and as unrestrainedly as they can, retreating only when seriously injured. Doves merely threaten in a dignified, conventional way, never hurting anybody. If a hawk fights a dove, the dove quickly runs away, and so does not get hurt. If a hawk fights a hawk, they go on until one of them is seriously injured or dead. If a dove meets a dove, nobody gets hurt. They go on posturing at each other for a long time until one of them tires and decides not to bother anymore, and therefore backs down. For the time being, we assume that there is no way in which an individual can tell in advance whether a particular rival is a hawk or a dove. He only discovers this by fighting him, and he has no memory of past fights with particular individuals to guide him. Now, as a purely arbitrary convention, we allot contestants points. Say 50 points for a win, 0 for losing, minus 100 for being seriously injured, and minus 10 for wasting time over a long contest. These points can be thought of as being directly convertible into the currency of gene survival. An individual who scores high points, who has a high average payoff, is an individual who leaves many genes behind him in the gene pool. Within broad limits, the actual numerical values do not matter for the analysis, but they help us to think about the problem. The important thing is that we are not interested in whether hawks will tend to beat doves when they fight them. We already know the answer to that. The hawks will always win. We want to know whether either hawk or dove is an evolutionarily stable strategy. If one of them is an ESS and the other is not, we must expect that the one which is the ESS will evolve. It is theoretically possible for there to be two ESSs. This would be true if, whatever the majority strategy of population happened to be, whether hawk or dove, the best strategy for any given individual was to follow suit. In this case, the population would tend to stick at whichever one of its two stable states it happened to reach first. However, as we shall see, neither of these two strategies, hawk or dove, would in fact be evolutionarily stable on its own, and we should therefore not expect either of them to evolve. To show this, we must calculate average payoffs. End quote. Okay, so at this point he goes in and he does a little bit of math, and he calculates the different average payoffs for hawks and doves meeting each other. I'm not going to go into the math of it, but essentially the end result here is that if you have a population of hawks and some doves enter the population or evolve or what have you, somehow enter into the population, the doves will be very successful because the hawks will always fight each other until one of them is seriously injured, which is a severe penalty. Whereas the doves, although they will lose every fight, they never get seriously injured because they always run away. And so as running away, they're always able to continue to live to fight another day, and they're able to acquire resources elsewhere. They're able to reproduce. Essentially, the payoff mathematics would indicate that doves would enter into the population because they have a high survival in a world filled with hawks. All the hawks are always running the risk of being severely injured. On the other hand, if you have a population full of doves, a hawk or a few hawks entering into the population would begin to take over because they would win every single battle against the dove all the time, and therefore they would acquire the points, which in this, translate to access to resources and access to mates and things like that. And so the hawks would begin to infiltrate the society of doves, and the doves would begin to infiltrate the society of hawks. And so neither of them are exactly stable. So then he says, quote, "The way I have told the story, it looks as if there will be a continuous oscillation in the population. Hawk genes will sweep to ascendancy. Then, as a consequence of the hawk majority, dove genes will gain an advantage, an increase in numbers, until once again hawk genes begin to prosper, and so on. However, it need not be an oscillation like this. There is a stable ratio of hawks to doves. For the particular arbitrary point system we are using, the stable ratio, if you work it out, turns out to be 5/12 doves to 7/12 hawks. When this stable ratio is reached, the average payoff for hawks is exactly equal to the average payoff for doves. Therefore, selection does not favor either one of them over the other. If the number of hawks in the population starts to drift upward so that the ratio is no longer 7/12, doves would begin to gain an advantage, and the ratio would swing back to the stable state." End quote. Okay, so basically you have a situation, it sounds kind of like economics here, with this kind of equilibrium that occurs where any fluctuation away from this 5-to-7 ratio, 5 doves to 7 hawks ratio, would change the payoff scale, the average payoff of being a hawk versus being a dove, what's going to net you on average more points in his point scale system. Any deviation from that ratio is going to cause one or the other to gain more average points, and so the population would swing in that direction until it reaches that equilibrium again. So that's what he essentially sees as this evolutionarily stable strategy. The population would look like he describes, 7 to 5. However, he then goes on to talk about, and I'm not going to read this section, I'll just describe it to you, but he basically talks about how you don't necessarily have to envision a scenario whereby any individual unit in this example is either a hawk or a dove. You might consider that a similar evolutionarily stable strategy would be for any particular individual to behave like a hawk 7 out of 12 times and behave like a dove 5 out of 12 times. And if every individual had that same propensity toward behaving like a hawk 7 to 5, then that would be a similarly stable strategy, a similarly evolutionarily stable strategy. And any individual born into such a scenario that didn't follow the 7 to 5 ratio would therefore be at a disadvantage. Their average payoff would be lower than those with the 7 to 5 ratio of behavior. And so it becomes a sort of a behavioral array, a set of behaviors that becomes the most evolutionarily stable. But then you say, well, can we make this more complicated? I mean, you've already said you've got a behavioral pattern of 7 to 5, but then he postulates later on something like he calls the retaliator, where once an individual would behave like a dove until the opponent begins to behave like a hawk, in which case they would respond by behaving like a hawk. So that the scenario, not just that it would, 7 times out of 12 they behave this way and 5 times out of 12 they behave that way. The more specific the strategy becomes, the more that some particular creature would be able to gain an advantage. And that creature that has that particular strategy would then pass on that behavioral strategy to others as it reproduces. And so none of this, what's interesting here is that none of this relies upon any sort of right or wrong or morality as to whether it's right to behave like a dove and wrong to behave like a hawk or anything of that nature. And it's certainly not the case that there's some sort of supernatural guide to say, well, if you didn't have this this code of behavior that is associated with this supernatural, that there's a revelation, it's written in this book or whatever that you're supposed to behave like a hawk 7 times and a dove 5 times. And if you didn't have this direction from this religion, you wouldn't know how to behave, whether to be a hawk or a dove or what. You would not know what to do. The point here is that the behavioral strategy is a simple mathematical reality. The behavioral strategy is an evolved system. And if you believe in the process of evolution, which is very straightforward, then this is the natural result of evolution, the evolution of behavior patterns. And so I think that's pretty cool. You can really kind of break this down mathematically. And the next book that we're going to look at is going to go into some very similar details about the evolution of behavior patterns. But I wanted to talk about that to introduce the evolutionarily stable strategy, which is so important when we talk about human nature. Because human nature is what it is because it is an evolutionarily stable strategy. So that's about all I wanted to talk about in this book. Again, there's so much other stuff in this book that's really interesting, and is ultimately, the rest of the book is derived very much from that evolutionarily stable strategy. Like I said, he talks about mating, child rearing, but mostly within the animal world. But all these sorts of behaviors in the animal world that can be understood as evolutionarily stable strategies, whether it's aggression or altruism or what, and a lot of it is their sort of relationship, just like the hawks and doves, that sometimes you be aggressive and sometimes you be altruistic, and the more you can fine-tune the behavioral pattern to the environment around you to know when to do this or when to do that, the more evolutionarily successful you will be. And so those sorts of fine-tuned strategies become more populated within the general gene pool. So that's all for this show. Check me out on Twitter. That's my main social media access, but I'm also on Facebook as well. And you can find me on iTunes and Google Play and on YouTube and on CastBox and on Stitcher. And I know there are a few others that I'm not thinking of off the top of my head. But subscribe to the show, leave some feedback, and come back next time. Thanks for tuning in. Bye.